everyone. Before we started our presentation today, I wanted to take a moment to acknowledge each of the members of our group. To create this presentation, we decided to split our group into a research team and a presentation team. The research team compiles all the information to solve the question proposed to us by Dr. Forster. The presentation team, on the other hand, condensed the work of the research team in order to create an easy-to-understand yet engaging presentation for you all. Our research team consisted of Nastasia Demjanovic, Carly Hovamo, Gianella Tang, and Michael Tovar, while our presentation team consisted of Christina Forbes and Rin Ruby. That's me, by the way. Now, without further ado, I'll pass things over to Christina so that we can get this presentation started.
Thank you, Rin, and hello everyone. Thank you for joining us today. We are very excited to share with you our plan to experimentally redetermine the lattice energy of potassium chloride. Not only will this allow us to compare our experimental values to known literature values to confirm the effectiveness of our procedure, but it will also hold importance to real-world applications as we will later explore. Let us begin with a review of lattice energy. Lattice energy describes the internal energy that corresponds to the formation of 1 mole of an ionic compound from its gaseous substituents. Some literature may define lattice energy as the reverse process, associating it with the energy required for an ionic compound to convert to its constituent gaseous ions. This second definition will give a value with the opposite sign but equal magnitude as the value related to the first definition. For the purpose of this presentation, we are describing the process of gaseous ions forming the ionic solid. The electrostatic attractions that form between the anion and cation give rise to the high stability observed in ionic compounds, and thus the lattice energy is indicative of the relative strength of these bonds. Generally, the higher the charge of the ions in the compound, the higher the lattice energy of the compound, which also corresponds to higher stability. This is supported by the terms in the numerator of the Born-Landa equation, where Z plus is the modulus, or positive value, of the positive charge, and Z minus is the modulus of the negative charge. Once again, the higher the charge of the ions in the compound, typically the higher the lattice energy corresponding to that compound. While it is a useful value that describes the stability of the bonds, there are, unfortunately, complications that arise in directly measuring the lattice energy, as it is not exactly plausible to form an ionic solid from gaseous ions, even in a laboratory setting. Luckily, we can utilize the Born-Haber cycle to ascertain a value for lattice energy by employing accepted values for the enthalpy of atomization, the ionization energies to form the cation, and the energy associated with the attachment of an electron to form the anion. This leaves us with the task of calculating the heat of formation for the reaction. The application of Hess's law allows us to compare the standard enthalpy change of formation of an ionic compound to the enthalpy required to create gaseous ions. In case you secretly need a reminder about Hess's law, it describes how the total enthalpy of a reaction is equal to the sum of all changes in enthalpy, regardless of how many steps are involved. This shows that enthalpy is a state function and does not depend on the path of the reaction. I am sure most of our audience today was just absolutely thrilled to learn about this in Chem. So, you may ask, why do we even want to calculate the lattice energy of potassium chloride? Well, to answer your theoretical question, in order to withstand the effects of corrosion in certain environments and the effects of severe forming procedures, many metals and alloys such as steel, aluminum, and magnesium are often treated with an organic coating. These organic coatings commonly consist of molybdate or phosphate-doped polypyrroles and polyaniline. Organically coated metals have applications in both military and civilian, automotive, aerospace, microelectronic, and biomedical industries. The image below shows a steel sheet plated with an aluminum zinc layer as well as an organic film. The organic film combined with the aluminum zinc layer provides extra protection against corrosive media such as oxygen and electrolyte. This enables the metal to be both mechanically and chemically stable. While organic coding is a very useful technique, its effects can be essentially nullified by certain ions that are capable of delaminating, or separating, the organic layer from the metal layer. Studies conducted by Lighthizer et al. Indicate that defects in cations and anions in the crystal lattice structure weaken the adhesion of the organic layer. It was determined that the lattice energies of metal chlorides are one of the primary factors that affect the rate of delamination, with research showing that different sized particles correspond to different lattice energies. The lattice parameter can be defined as the distance between 2 points on the corners of a unit cell. Research conducted by Sharma et al. Indicate that potassium chloride nanoparticles have significantly larger lattice parameters than their bulk counterparts. It was deemed that intrinsic defects are responsible for the expansion of the lattice parameter of potassium chloride nanoparticles. These defects were introduced through ball milling, a method that grinds materials into an extremely fine powder, with the defects consequently generating surface stress on the nanoparticles. Both Schottky and Frankel-type point defects may develop from ball milling. Schottky defects describe vacant lattice sites in a crystal lattice structure. Either anions or cations can be vacant. In fact, in order to maintain electron neutrality, equal numbers of cations and anions must be missing from the crystal lattice. Frankel defects describe a situation in which the smaller ion of an ionic compound is present in a site from which it is normally absent from in the ideal version of the lattice. This may arise when there is a significant difference in size between the cation and anion. For example, a cation may migrate from its octahedral hole to a tetrahedral hole, where it would not typically be found. Since it is simply a migration of an ion and not total absence, the electron neutrality of the compound remains unaffected. The increase in lattice parameters affects the size of the molecules, as seen in the Born-Landa equation.
Thanks for that wonderful introduction, Christina. Now, it's my turn to introduce you all to the method we intend on using to determine the lattice energy of KCl. To reiterate a few key points that Christina mentioned during the very beginning of this presentation, it's impossible to experimentally determine the lattice energy of a substance. This is due to the relative difficulty associated with isolating ionic species. Though we can't directly determine the lattice energy of KCl, we can indirectly determine the lattice energy of KCl using the Born-Haber cycle. This is achieved by determining the enthalpy of formation of a given ionic species, in our case, KCl. Calorimetry is the only experimental method which allows for the determination of the enthalpy of formation of a substance. However, for ionic compounds, it's quite difficult to directly measure the enthalpy of formation of a substance. Luckily for us, for ionic compounds such as KCl, the heat of formation can be determined indirectly by measuring its heat of dissolution. This is achieved using a branch of calorimetry called solution calorimetry, in which the heat released during the dissolution of the compound is measured. This measurement eventually leads to the determination of the enthalpy of formation of the substance. A paper written by George Kim discussing the enthalpies of formation of intermetallic compounds and other inorganic compounds suggests an equation by which the enthalpy of formation can be determined through the enthalpy of dissolution. The calculation proposed by Kim is associated with the dissolution of compounds containing metals with low melting points. However, with some further reworking, it may be applicable to ionic compounds, allowing us to determine the heat of formation of KCl. Alternatively, the lattice enthalpy of KCl can be determined using yet another extension of Hess's law. In this calculation, the enthalpy of formation is determined by adding the enthalpy of dissolution of KCl with its enthalpy of hydration. Because KCl does not easily form hydrated complexes, we can use values from the literature rather than determining this value experimentally. The following slide provides a step-by-step method regarding how to take calorimetric measurements. Though I will not be reading each and every step listed on this slide, I will go over the general principles which dictate calorimetry. When a compound dissolves, it'll either absorb heat from the surroundings or release heat into the surroundings. The direction of heat transfer indicates whether the dissolution process is endothermic or exothermic. Calorimetry relies heavily on the first law of thermodynamics. For an isolated system, the total energy of the system must remain constant. Therefore, the amount of heat absorbed or released by the dissolution of the compound must be equal to the amount of heat transferred to the surroundings. Thus, by measuring the change in temperature of the surroundings, we can determine the enthalpy of dissolution of the system, in our case, KCl. Assuming the heat capacity of KCl is known, we can determine the amount of heat released during its dissolution using the following equation, where Q is the amount of heat released by the system, M is the mass of the sample, C is the specific heat of the sample, and delta T is the change in temperature of the surroundings. Excluding the costs of quote-unquote standard lab equipment such as weighing scales or glassware, the cost associated with determining the lattice energy of KCl is quite reasonable. As shown on the current slide, the solution calorimeter provides the greatest contribution to the total amount of money needed to determine the heat of dissolution of KCl. The additional costs associated with experimental determination of the lattice energy of KCl come from the nitrogen gas tank, which is necessary for the operation of the calorimeter, and the KCl samples themselves. Tallying up these prices result in a total cost of approximately $15,300 for the determination of the lattice energy of KCl. Of course, this price can vary depending on where you decide to purchase your materials from. Our group decided to use the prices specified by Fisher Scientific due to its reputability and because it's a brand common to the laboratories here on campus.
Thank you, Rin. Now, to review the contents of our proposal. It is impossible to directly determine the lattice energy of potassium chloride experimentally. However, using the Born-Haber cycle, we can indirectly determine the lattice energy of potassium chloride by determining its enthalpy of formation. This can be achieved using calorimetry to find the enthalpy of dissolution, which can then be used to calculate the enthalpy of formation, which, relatively speaking, is a rather cost- and time-effective determination method. By experimentally redetermining the lattice energy of potassium chloride, its effect on the delamination of organic coatings can be determined. This valuable research can be further applied to the various industrial applications of organic coated metals. Thank you for joining us today. Please feel free to ask any questions.
Hold up, Christina. Before we start the question period, I think it's important to acknowledge all the books, websites, and articles that we drew information from. Though I won't mention each source by name, we're not that desperate to fill the allotted presentation time. I do encourage any of you who are interested to take a look at the following sources. I personally found the article regarding the delamination of organics coatings super interesting. Finally, I would like to once again thank all the members of our team. Each of our respective roles are listed on the slide here. Now, let's happily reunite with our class back on WebEx to answer any burning questions they may have.